variation. Once you've looked at data, we can also start to calculate some numbers that mathematically describe some summary of your data. Now, these summaries are going to be incomplete. A mean doesn't capture everything in your data set. Neither does a standard deviation or median or so on. But they can be really informative, particularly when we start to get to hypothesis testing and we want to know if there's, say, a significant difference between the mean of one group and the mean of another. We can categorize descriptive statistics as measures of centrality. So what is the most common value in your data set, or what is the mean? Basically, where is the center of all of that variation? Are all the data points relatively close together? Are they spread out? Are they uniformly spread out? Or is variation kind of weird and all over the place? These are all things that we can not only see and get a general feeling of with data visualizations, but we can put numbers on them using descriptive statistics. It does matter what type of data we have. So if you're looking at non-numerical data, then your data type matters. Then you're limited, like you can't exactly go about calculating a mean for Toyota and Audi and Subaru. Instead, we have count data. So in our data, how many instances are there of Toyota and Audi and Subaru and Hyundai? And with that, we can calculate out proportions or percentages or ratios. So are there twice as many Toyotas as Hyundais? Are Subarus equal in frequency to Audis? Those are the types of measurements we could get with categorical data. With numerical data, there's a whole lot more we can accomplish. There's the mean, and this is where we add up all the values in our data set, and then we divide by the number of values in that data set. Median is just ranking all of your data values and picking the middle one. If you have an odd number of samples in your array, then the middle sample ranked is going to be your median. If you end up having an even number in your array, then the median will be the midpoint between those two central figures. So if the two central numbers, if you have 10 data points, then that would be, let's say, your fifth and sixth data point, or no, sorry. Yes, your fifth and sixth data point. Let's say our values are 10 and 20, then your median might be 15. And then mode, what is the most common value? The R code for calculating these it's straightforward, is essentially mean, median, mode, or summary, which gives you a lot of these, plus the name of the column. Now keep in mind, if you are in your working directory and working within a data file or a data frame, let's say your data frame's name is child heart surgery, and you want to name your column, then it's probably going to be child heart surgery $ name of column within that function. Now these differ in how robust they are. And robustness is a measure's resilience to changing single values. So if you have a list of 100 values, and all of a sudden you take one of those 100 values and you change it from 10 to 40 billion, how much of an impact is that going to have on the overall measurement? So which of the following measures do you think is the least robust? Pause the video, I'll give you some time to think about it, and the answer in 3, 2, 1, and stop. All right, which one's the least robust? Well, that is going to be the mean. Median and mode are quite robust because they don't rely on the amounts, the total amounts of all values. Right? We're just ranking things. So median is going to be that middle value. If your highest value now all of a sudden quadruples in size, that actually doesn't change your median at all. And the same thing goes with mode. Whereas if you change one value, that might minorly change your mode if that's a common value, but usually doesn't. However, a mean can be very highly skewed. That's why when we're looking and talking about income in a geographic region, you probably don't want to use mean. The mean is going to make it look like the average income is way higher than in reality it kind of is, because it's being skewed by some small number of individuals with exceptionally high income. That's why we often use medians in this sense, where medians are going to be more robust. What information does mean contain that median and mode don't? Well, we use mean and we often gravitate towards it, even though it's less robust, because mathematically it still does contain quantitative information about every single data point. So every single data point's value is being added together. In, let's say, median, we care about rankings, all the information that you would get from ordinal data, and then we pick that value. So in a mean, we're getting all the information you would get out of numerical data. Median and mode, now we're kind of getting ordinal style information. So there's just a little bit less of it. But just to show that this idea of Anscombe's quartet, this is a data set where we have 4 different plots that have different values for X and Y axis. And if you were to go ahead and plot a scatter plot of X1 and Y1 and X2 and Y2 and so on, you would get the exact same summary statistics for all 4 of those. The mean is the same, the sample variance, the correlation, the regression, all of it is identical. But don't forget, even though right now we're talking about descriptive statistics, you still need to always plot it out. So these are those 4 showing us 4 very different relationships that would have a huge impact on whatever biological system we're examining. Now let's talk about how we can start to use these things to measure variation. We began by talking about the most common measures of centrality. Now let's look at measures of variation. So we're beginning with this. What kind of figure is it? And 3, 2, 1, it is a scatter plot. Now, this could be a line graph. Because the x-axis is time, you could make this very easily into a line graph. You would just have to draw and connect the dots between all of the time points in order along the x-axis. And you could do that. But for now, it is just a scatter plot. This is going to be data from 10 individual plants, and the y-axis is yield of fruit in grams. So different time points, we collect fruit off trees, and this measures how much fruit we get. Now, how do we calculate centrality of fruit mass in this case? Take a second to consider, and 3, 2, 1. Well, we could calculate the mean. We have values of mass in grams for each one of these 10 dots, so we can use that to figure out the average. And this is, if we want to make a prediction, going to be the most likely value moving forward. Right? That if we want to predict future fruit yields, which as a farmer, that could be a pretty good idea. Well, as of now, given this data and nothing else, choosing the mean would be a pretty good model. How can we measure the total variation around the mean? Because if we have a lot of variation and every year there's a ton of variability in fruit yields, then this predictive model might not be all that effective. However, if we have a small amount of variation and every year is pretty much the same, well, then this estimate gives us a lot of information. So how do we put a numerical value on this variation? So I want you to look at this, pause it, see if you can think mathematically, how would we measure the total amount of variation here? How do we calculate the total distance of each point from the mean? Well, we could calculate something known as a residual. And a residual is going to be the distance on the y-axis between some sort of model, in this case, the horizontal line at the average, and each individual data point. So just moving up and down, perpendicular, we see the distance between each data point labeled as y sub I, and then y bar being that relationship, so the mean. So we just take the mean, the observation, we subtract the mean, and that gives us our residual. And the farther that number is from 0, well, then the greater amount of variation we have for it. What would be wrong if we just sum up all these values? So if we were to calculate the difference between observation and mean for all 10, add them together, we get a value. What's problematic about doing that? 3, 2, 1. Well, what's problematic is that the ones that are lower are going to have that are on the bottom, if I go back a second, the y sub i's that are below average, they're going to end up giving us a low number minus a larger number, a negative residual, and the ones that are above the mean are going to give us a positive residual. If we're adding a bunch of positive and negative numbers, they're just going to end up canceling out. So even if we have a large spread, a ton of variation, if there's the same amount of spread on one side and another, and we just sum the residuals, we end up getting an amount of variation of 0, which is not very informative or accurate to what we're seeing. So what we can do is we can take these deviations, these residuals, and instead of just summing them, we can sum their squares. Now, when we apply the same mathematical operation to everything in the exact same way, we're not losing the relationship between them. So you can take a bunch of numbers and then square them all. Their mathematical relationships are the same. You can cube them all. You can square root them. You can take the natural log of them. As long as you do the same thing to everything that you're working on, you don't lose the mathematical relationship. But you can start to make things work in your favor, like, say, making everything positive. If we have two negatives, like a negative number squared is a positive number squared is a positive. This would be quite similar to as if we were to take the absolute value of the difference. In this case, we are summing the square deviations, which should then net us an overall positive number. So in this case, why don't you just go ahead and use this basic equation, the total sum of squares, and then calculate for a relatively straightforward measurement. And 3, 2, 1. All right, so looking at this, I haven't thought about this calculation for a while, but we need to know our mean. And for this array or vector, the mean would be 3. So the squared difference of for each one of these, we would have, well, for 3, it'd be 0. 3 minus 3 is 0. For 2 and 4, that squared value would be 1. And then for the other two, the difference is 2, which would be 4. So 4 plus 1 plus 0 plus 1 plus 4, or the answer of 10, which we see is option C. Now, variation in continuous numerical data we can measure in range, interquartile range, variance, and standard deviation. Later on, we'll get to standard error, but that's a bit different, and so we haven't kind of gotten to that part of class yet. But for now, we're going to stick to these 4, and the R code for most of these is summary.list data $column. The range, just what's your maximum minus what's your minimum value. What is range most useful for? Blank. I would say that B is probably your best answer. Now, C is possible if you have a very well represented, incredibly large sample size. And then you could say, okay, we're probably not going to find anything significantly outside of this range. But otherwise, functionally, it establishes the scale of your figure axis, but it is not going to tell you the structure of the variation within your data. Like, let's say you have 100 numbers, all of them are 50, except one number is 1 and one number is 100. That means you have a range of 99, 100 minus 1, even though most of your values are identically 50. So your range can hide the nature of much of that variation, but it's still a good thing to know. IQR, this is called interquartile range. So instead of using the difference between the highest and lowest, it's going to be the value at the 75th percentile and the 25th percentile. The idea being that in doing this, we're now ignoring the outliers so that we can see the range that is really important to most of our data. It's a lot more robust than, say, just basic range is. Which figure type uses IQR? And that would be A, the box plot. You can see that here. We have the box with the median, the lower and upper quartile, min and max, and sometimes you'll even see outlier outside of the box. You'll often see outlier data points as single dots. Now let's look at variance, which is the equation that you see in front of you now. It's very similar to the sum of squares. The main difference now is just instead of dividing, more or less we're kind of taking the average. We're dividing by the sample size, n minus 1. It's not just n. We won't go into the details of why we're dividing by n minus 1 rather than n. It has to do with something called degrees of freedom. We're not going to get into that now. But the idea is that if we have a measure of squared difference for every single data point, instead of knowing the total amount of variation, it might be more useful to know, well, for any given data point, what's the average amount of variation? What's the average squared difference? And that's what variance gives us. Now, you want to measure the variance of lung volume in patients. What unit is variance in? Well, in this case, we have a unit that is lung volume, meaning centimeters cubed, but you can already see that we square that value in the equation. That's why variance is labeled as s squared. So when we calculate variance, the units that we get from our equation is the squared of our unit. In the case of cubic centimeters, that's cubic centimeters squared, or centimeters to the sixth. I don't know how to visualize centimeters to the sixth in my mind. It doesn't make any sense to me. So even though variance is straightforward, this is a way of representing variation, the average amount of variation. It's in a unit that doesn't match our data. This is why we prefer dealing with standard deviation, which is the square root of the variance. Because not only are we getting a measure of this average, but we're putting it in the units of our data. If the only difference between variance and standard deviation is that we're taking the square root, why don't we almost always prefer to use the standard deviation over variance? Well, I think I let the cat out of the bag. It's the same units as our data value. A is going to be the best answer for that. Rank each according to the amount of information it gives you about your data set. I think in the end, if you have a box plot and you have all of the information, which provides you with range and IQR, you might say that that gives you more. But for this, in this wording, I would vote for standard deviation, because in standard deviation, we are accounting for the value of every single data point. Every single data point is adding into and impacting in some way our measurement. It's containing that information, just like mean does over median, whereas range or IQR only really cares about particular values, either your highest or lowest, or your 25th and 75th highest. Standard deviation calculates using every single data point. So C is going to have the most mathematical information in it. All right, that is it for this video. So have a great weekend, 3-day weekend. I will see you on Wednesday in class. And then if you are in a Monday section, feel free to please attend any other section next week, since you won't be able to attend yours. I'll also have my office hours on Friday, and next week I will announce when I will be rescheduling my Monday office hours, since they won't be happening because of the holiday.